Hello everyone and welcome back again in our channel. Today we will talk about the exact differential equation, which is the last type of first order linear equation. And the definition: it is a differential equation of the form m x y dx plus n of x and y dy equals 0, where m and n have to be continuous and have continuous first partial derivative on some region in the xy plane. Then it is exact if and only if the partial derivative of m with respect to y equal the partial derivative of n with respect to x. So if these two functions are not equal, then in the next video we will use another method called integrating factor method, how to solve it. So here, exactness criteria: assume a function like a surface, and this surface in the space z equal psi of x and y, and this surface is cut by a plane. Then the points of contact with that plane will create a level curve, and the equation of this level curve is psi of x and y equals c, and then we derive both sides. So c will be zero, and multiplying both sides by dx, so this will be cancelled, and we got d psi equal partial of f with respect to partial of x dx plus df over dy, the partial multiplied by dy equals 0. This is equation 1. For our original function psi of x and y equals c to be continuous and differentiable, we should have this partial derivative, the mixed partial of x and y equal this partial of y and x. And here m we have already, so we need to take the partial again with respect to y, because here we have the x and here we have the y. So again we take the partial derivative with respect to y and with respect to x, and equate them and see if they are equal, which means our equation is exact. So we find the partial derivative of m with respect to y and the partial derivative of n with respect to x, and if they are equal, then our differential equation is exact, which means that our potential, the original function we are trying to find, is continuous and differentiable on a certain region R in the xy plane. How to solve the exact differential equation? Here we have example, and we will go step by step how to solve it. So first, put the differential equation in the differential form. Here is our differential form, equals 0. There is plus sign here. Find m, the function m, and n, and take the partial derivative of m with respect to y and n with respect to x. Here, this is the function m equal 2xy. So partial of m with respect to y equal 2x. And here is n, 1 plus x squared. The partial of n to the dx to the partial of x equal 2x. Since they are equal, see, because here 2x and here 2x, so our differential equation is exact. Find the potential function by integrating m with respect to dx or n with respect to dy, either one. But we go with the easier one, which is easy to integrate and solve. We go with that function. But both of them are correct. Here, so here our original function equal m of x and y dx equal, and instead of adding a constant of integration, we add function of y because we are integrating with respect to x dx. So we consider the function of y as a constant instead of putting constant of integration like c or k, and this is equation 1. Instead of adding a constant of integration, we add function of y. Differentiate both sides of equation 1 with respect to y and equate it to the function n of x and y. And here's our differentiation. Plus f prime of y. And here's our n function. So from this equation, we got f prime of y equal 1. This is equation 2. Integrate equation 2 with respect to y. Here's our integration. And f of y equal y plus c1. Here is c1 is constant of integration. So if we add it or we don't add it, there is no problem because this constant will be observed by another constant at the end of our solution. And it's still the same. When we use the initial condition, we find that constant. So now we substitute f of y from step 5 in equation 1 here. In equation 1. Psi of x and y equal x squared y plus c1, which is the solution to our potential function, our original function that we are trying to find. Therefore, x squared plus y plus c1 equals c. Remember, the equation of our level curve is psi of x and y equals c. So here we put the c to this function. We move c1 to the right-hand side of the equation, and again, c minus c1 will be another constant, and we call it k. So you can see that if we add or we don't, we still have one constant. And we try to find the implicit solution for y, and then we find k from our initial condition, which says at x equal 2, y equal minus 5. So just we plug these two values and we found k equal 25, and this is the final formula for y, the solution to the original function, 25 over x squared plus 1. In the next video, we will talk about another method if the partial of m with respect to x doesn't equal the partial of n, the partial of m with respect to y doesn't equal the partial derivative of n with respect to x. If they are not equal, we will use another method called integrating factor. So see you in the next video.